Hey guys, well I'm going to move on to the next section. This is section 12.3, Logarithmic Functions, and we're up to page 19 of our chapter 12 handouts. So, objectives for this section are to graph logarithmic functions, to convert from exponential equations to logarithmic equations and vice versa, solve logarithmic equations, and also just to find common logs on your calculator. And really, I think we should just add kind of a little another objective at the very top, which is to explain what is a logarithm. Okay, maybe you're familiar with them, maybe you've done calculations with them before. What I really want to do is just make sure that you really understand what a logarithm function is. So we're going to start by looking at an exponential function. Y equals 2 to the x, or if I even write it in function form, maybe I should have done that, we would say f of x is equal to 2 to the x. That's equivalent, of course, to y equals 2 to the x. And we've looked at this before. Actually, if you go back to page 3 of these chapter 12 handouts, we already looked at that function and we plotted it. Okay, so we're going to start actually on the next page here by plotting it again. All right, so I'm going to scoot to the next page and go over the instructions. All right. Okay, so for the function f of x equals 2 to the x, I want you to start down here by calculating the values of f of x equals 2 to the x. And we've done this before. I think I added a couple additional values in here. And I want you to just calculate these to decimal form, because then you're going to end up plotting them. So, for example, if x equals -3, then y equals 2 raised to the -3. And then, of course, you can just do that on your calculator, or you can know that that's the same as 1 over 2 to the +3. In other words, 1 over 8, which in decimal form is exactly 0.125. All right. So your first ordered pair for the function 2 to the x is -3, 0.125. So if we want to go ahead and plot that, that's at -3. And then 0.125 is half of a quarter. So here's half. So a quarter is about here, half of that. So it's about there. Okay. So calculate all these values for f of x equals 2 to the x, plot them, and then make a smooth curve for your plot. And again, this should be no problem. You've already plotted this function. And then what I want you to do is I want you to find the inverse function simply by reversing the ordered pairs. We learned that in the previous section. That's the easiest, simplest definition of an inverse function, is you just take xy and you reverse it. So in other words, here I had a y of 0.125, so now that is going to become the x for the inverse function. And I had -3 for x, so that's going to become my y. So I've just taken this ordered pair and reversed it. So this pair is a member of the inverse function. So after you've got these, then create this column of ordered pairs and plot them as well. So for example, I'll go ahead and plot this first point. X is 0.125. So again, that's just here. It's pretty close to 0, and y is -3. So it's about here. Okay. All right, so pause this, go ahead, fill this table out, reverse your ordered pairs, fill this out, and make both plots. Then I'll come back, make sure you've got all the right answers. All right, so let's see on this one. 2 to the negative 2 is 1 over 2 to the 2. 1 over 4 is 0.25. Let's go ahead and just plot these points as we go along. So negative 2.25 is about here. 2 to the negative 1 is just 1 over 2, 1/2, or 0.5. So let's plot that point. Negative 1, 0.5, about there. 2 to the 0 is 1. Okay, so that's the point 0, 1, which is right there. 2 to the 0.5, if you just do that on your calculator, it's about 1.414. So x is 0.5, and then 1.414 is just a little bit less than 1.5, so about here. 2 to the 1 is 2, so the point 1, 2, right there. 2 to the 1.5 is about 2.828. So now we're at x is 1.5, which is here. Y is 2.828, so about there. And then of course 2 to the 2 is 4. All right, so we've got the point 2, 4. All right, and then the goal would be to connect these in a nice smooth curve. This is probably not going to go well for me, but I'll do my best. And actually, that exceeded my expectations. All right. And maybe you can see just from looking at that, the domain of this function, I can put any value of x in there that I want. So the domain is just simply all real numbers, negative infinity to infinity. And then the range, the output, the y values, maybe you can see by inspection, as x continues to get more negative, like here, if I put a more negative number in, it's just going to be 1 over a bigger number. It's just going to get closer and closer to 0. So in other words, it's going to get close but never reach 0. And then obviously this is just going to keep going up and up. So the range is 0 to positive infinity. All right, so now let's just switch all those ordered pairs and write the inverse function, basically. So this is 0.25 and negative 2. Let's go ahead and plot that. Let's see, so 0.25, it's about here, and negative 2, so it's about there. 0.5 and negative 1. Okay, let's plot that. So 0.5, negative 1, about there. 1, 0 is there. 1.414 and 0.5. Okay, let's plot that. So 1.4, just a little bit less than 1.5, and then it's 0.5, so about there. Let's see, 2, 1 is there. About 2.828 and 1.5. All right, 2.8, so that's kind of about up here, and then 1.5, so it's about here. It's a little bit high on that one. Okay, about there. And then 4, 2. All right, so 4 comma 2. And again, let's try to connect those with a nice, oops, I totally missed there. Smooth curve. It's going to be kind of like that. And like this. And that's going to keep going down and down and getting closer, but never touching the y-axis. Okay. So the domain, in this case, what values of x does it look like I can put in? Well, it looks like, you know, this is never going to cross the y-axis or get negative. So it looks like the domain is just positive numbers. So in other words, 0, comma infinity. But the range, well, this is going to keep going down, this is going to keep going up. So it looks like I can end up getting any y value out. So in other words, the range is all real numbers. Okay. And you can just cross, we're not going to use that column. I adapted this from a different class. All right, so we have a plot of the inverse function, and as before, when we looked at inverse functions, you'll notice I had plotted the line y equals x, and if you recall, you know, the inverse functions, each point is symmetric across the line y equals x. So if you just check out a few of our points, you'll see that that's the case. Okay. All right, so now that we have a graph of the inverse function, I'm going to delete this and I'm going to go back to the previous page. Here. All right, so on the next page, you know, we just plotted the inverse of the function y equals 2 to the x. Now let's try to find the inverse analytically using the methods that we had learned in the previous section. Okay, so we just write the function, and again, I could have had f of x equals 2 to the x, but we would replace the f of x with y. So the function is y equals 2 to the x. And then, just like we did before, we swap the x and the y. So we get x equals 2 to the y. Okay, and remember, that is the inverse. Okay. But the problem is, again, we don't usually write our functions as x equals stuff. We want to write it as y equals stuff. So we want to be able to solve this equation, this inverse, for y equals stuff. Okay? But the problem is, we don't know how to do that. We don't have a method yet, because this y is up in the exponent, and we don't know how to solve to get it out of that exponent so that we can have y equals stuff. So, you know, we could try just describing the inverse function in words. Okay, now I'm not going to write this out because it takes me too long with this stupid pencil, but I'll say it a couple times. So if we wanted to describe the inverse in words, we could say something like y equals the exponent to which 2 must be raised to obtain a value x. Okay, one more time. We could describe it in words as saying y equals the exponent to which 2 must be raised to obtain a value x. Whew. Okay, so that's really wordy, and that's not how we like our math stuff. We like our math stuff to be concise. So instead of doing it that way, we're going to just introduce a new notation, a new function called the logarithmic function. All right, called the logarithmic function. So for this inverse that we found up here, x equals 2 to the y, we're going to define y equals log base 2 of x. Okay? So, and again, in words, you would say that log base 2 of x. And I think I was pretty clear here, but just to clarify, that is a subscript. That 2 is a little subscript. Okay? And just a comment that the base 2 here appears in both functions. In the exponential function here, the exponent has a base of 2. Okay? And in the logarithmic function, the logarithm has a base of 2. Okay? All right, now, I know we literally just did this, but let's do a recap already, just to make sure we know what's going on. So we started with f of x, or y, is equal to 2 to the x. That was our function, our exponential function. We found the inverse. That was our first step right up here. Okay, so we found that the inverse, f inverse, okay, was x equals 2 to the y. So that is written as x in terms of y. And again, that's not really what we want. We want y in terms of x. So to do that, we had to use this new notation and write the inverse as, and I just don't have room. You have room right here. I'm just going to come off to the side. Write the inverse as y equals log base 2 of x. Okay. And these inverse functions, and when I say these inverse functions, I'm talking about these two, this and this, x equals 2 to the y and y equals log base 2 of x. Those two inverse functions are equivalent. They're the same exact thing. Okay? They both describe that same graph, the one of f inverse that you plotted on the following page. Okay? So the key thing here is that is what a logarithmic function is. It is the inverse of the exponential function. And essentially, a log is an exponent. It is just another way of writing it. Okay? When we, describe things up here, we said y is the exponent to which 2 must be raised. Okay? Well, that exponent to which 2 must be raised is also the logarithm, base 2. So a log is an inverse of an exponent, and it is also essentially an exponent itself. All right, I'm going to go on to the next page. All right, so let me get back to where I was. Actually, yesterday, sorry, I was working on this, and then I got distracted, and then I just decided to take a nap, and it was an epic nap. So anyway, my apologies. I'm going to finish this up this morning, I swear. So we had been looking at y equals 2 to the x. So that would be here, y equals a to the x, where a is some positive number. Then we found the inverse, okay? So over here we have the inverse relation. All right, and the first thing we did was we just swapped the x and the y. So again, on the previous page we had x equals 2 to the y, and that is the inverse. And then we said we don't like that. We like things to be y equals stuff. And in order to do that, we had to come up with this new notation so that we could write y equals log base a of x. Or on the previous page, we had log base 2 of x. Okay? So again, these two things, these two statements here are equivalent. They are both the inverse function to the exponential function. Okay? And that's all that they're saying down here. All right? That this side is the same. Well, these two things are just saying the same thing. They just swapped the directions. Okay? So this is, and it is the most important relationship here. A to the y equals x is equivalent to, it's the same thing as y equals log base a of x. Okay? Just like that. And again, that's exactly what we had before. We had, when we found our inverse initially, we had x equals 2 to the y, but then we wanted to solve for y equals stuff. So we transformed that equation into one that said y equals log base 2 of x. Okay. All right, so one of the objectives for this section is that you need to be able to graph these logarithmic equations. So for example, here's a different one. Graph this. Y equals log base 3 of x. All right, so the technique here is we're going to convert this logarithmic equation into an equivalent exponential equation. So let's just use our format up here. So what we have is y equals log base 3 of x. And we want to be able to plot that, but right now we don't have a method for calculating log base 3 of x. So we're going to convert it into an exponential equation. So you can probably see that if we, use the same format here, then this just becomes x equals 3 to the y. All right, so this is what we're going to plot. So we can calculate x if we pick our y's. So that's why in the table here, I've already picked the y's for you, and then you calculate the x and plot the ordered pair. So for example, for the first one, I picked y equals -3. All right, so then I need to calculate x. Well, x is going to equal 3 to the y, so in other words, 3 to the -3. So that's the same as 1 over 3 to the +3. Sorry, pencil is kind of chunky. So that's 1 over 3 cubed is 27. And if you just calculate that out on your calculator, you should get like 0.037. All right, so that's my first ordered pair. X is 0.037, y is negative 3. So it's hard to find 0.037. So these are in units of 1. 1, 2, 3, 4, 5. So I'm just practically right here at 0. And then I have to go down to y is negative 3. So there's my first point on this graph. All right, so why don't you go ahead, pause this, and then calculate the rest of these, plot the graph. All right, and then I'll come back in a moment. You can make sure you have the right answers. All right, so let's see. If y is negative 2, then x is 3 raised to the negative 2, or 1 over 3 to the positive 2, which is 1 over 9, decimal form 0.111. So 0.111, again, I'm just still really close to 0 here, and then we go down to negative 2. So, you know, about here. If y is negative 1, x is 3 to the negative 1. 1 over 3 is 1/3, so about 0.333. All right, so now we're at 1/3, so about here and coming down to negative 1. All right, 3 to the 0 is just 1. All right, finally a nice easy point right there, 1, 0. 3 to the 1 is just 3. All right, so we're at 1, 2, 3, 1, which is right there. 3 squared is 9. So now we're at the point 9, 2. And 3 cubed is 27. All right, so 27, 1, 2, 3. All right, so I'm going to do my best to connect these points. Well, okay, that's okay, not great. And then this is just going to shoot down to negative infinity along the axis. So it should look something like that. Okay. So again, you know, the key point here is, in order to plot this, convert it to an exponential equation. Because this we can calculate. This, for now, we can't, although we will learn how to calculate, say, log base 3 later in the chapter. All right, so next page, converting between exponential and logarithmic equations. And this is exactly the same relationship we just saw on the previous page. In fact, we just did this in order to make that plot. So let me just write this again. So if we have a to the y equals x, then that is equivalent to, same thing as, y equals log base a of x. All right, and this is the relationship that we're going to use to convert back and forth between logarithmic and exponential equations. So, for example, let's start with this one. 2 equals log base 7 of 49. So that is obviously a logarithmic equation. We want to convert that to an exponential equation. All right, so let's just take this and put it over here. So what we have is 2 equals log base 7 of 49. So we're on the right-hand side here, and we want to then switch it to an exponential equation. All right, so what we've got here is x is 49. All right, so in other words, 49 equals, and then the base is 7, and the exponent y is 2. Oh, yeah. 7 squared equals 49. We knew that. So in other words, this is equivalent to this. All right, so that's your equivalent exponential equation for this one. This is just 7 squared equals 49. All right, let's try the next one. So this is obviously an exponential equation, and in this case we want to convert it to a logarithmic equation. All right, so let's do the same thing. We've got 9 equals 81 to the 1/2. That's just saying 9 equals the square root of 81. So in this case, we're starting with this, and we want to convert this way. All right, so what do we have? In this case, we have our y, the exponent, is 1/2. And that is equal to log base. Okay, the base of the logarithm is always the same as the base of the exponent. So it's log base 81 of x is 9. All right? So this right here is your equivalent, oops, sorry, logarithmic equation. Okay? All right, so I've got a couple problems here for you guys to try. Just do exactly the same thing. In this case, you've got a logarithmic, convert to exponential, and here vice versa. So go ahead and pause for a second and try to do those on your own before you check the answer. All right, so for the first one, again, we're starting with a logarithmic equation. T equals log base 5 of 9. All right, so we've got T equals log base 5 of 9. And we want to go this way to an exponential equation. All right, so the base of the log is 5. So that's going to be the base of the exponent. All right, and then we need y up here. Okay, so that's t. So 5 to the t is equal to 9. All right, so that would be your exponential equation for this one. 5 to the t equals 9. And then let's see, on this one we've got an exponential equation. So we have 16 to the 1/4 equals 2. All right, and now we're converting this way. So our y, so that's, I'm sorry, I think I wrote that wrong. (16 to the 1/4 equals 2. I don't know if I said it right or wrong, but I definitely wrote it wrong. All right, so our y is 1/4 equals log base. All right, the base of the exponent is 16, so that's also the base of the log. So log base 16 of 2. All right. Okay, pause if you want. I'm going to scooch this down. Okay. To just show you 2 more properties of logarithms. All right, the first one is if you take the logarithm of the number 1. Log base anything of the number 1 is 0. Okay? And the reason is, if you convert this to an exponential equation, let me come on over here. So we've got a logarithmic equation. We've got 0 equals log base A of 1. And if we convert that to an exponential equation, all right, so our base is A, so that's going to be the base of our exponential equation. All right, so we've got A to the 0 equals x, which is 1. And we know that to be true because any number raised to the power of 0 is equal to 1. So that is where that logarithmic property comes from. And the second one is log base A of A. So the log of a number, you know, if you take the log of base the own number, is always equal to 1. And again, let's look at how that works over here. So we've got log base A of A is equal to 1. And if we convert that to an exponential equation, all right, so the base of the logarithm is A, so that's the same as the base of the exponent. So we've got A to the y, which in this case is 1, is equal to x, which in this case is A. So all that's saying is A to the 1 equals 1, which we also know to be true, because any number raised to the power of 1 is itself. All right, next page, solving certain logarithmic equations. So now we're going to learn how to solve certain types of logarithmic equations. And the technique that we're going to use is to just convert them into exponential equations. And then we can solve those exponential equations. So let me just write our relationship up here one more time, where we know that if A to the y is equal to x, okay, that is an equivalent equation to y equals log base A of x. All right, so for example, for the first one, log base x of 49 equals 2, and we want to solve x. X equals what? All right, well, let's come over here and write down what we've got. So we've got 2 equals log base x of 49. All right, and then we want to convert this to an exponential equation. All right, the base of the logarithm is x, so that's going to be the same as the base over here. And then here, the y is here, so x squared equals 49. All right, so if x squared equals 49, then just using the principle of square roots, take the square root of both sides and then apply a plus or minus. So x must equal positive 7 or negative 7. However, all logarithm bases must be positive. Okay, a logarithm with a negative base is just not defined if you look back at the definition of it. Okay, and that's where x started here is as the base of the logarithm. So therefore, it's not possible for x to equal -7. So therefore, the only solution that is possible is that x equals 7. Okay. All right, next example, find log base 81 of 9. All right, so this is just some number. So the technique for solving is just set this expression equal to x. In other words, we're just going to say, okay, well, x equals log base 81 of 9. And then take that equation, that logarithmic equation, and convert it to an exponential equation. All right, let me come back over here. So we've got x equals log base 81 of 9. And we want to convert that to an exponential equation. All right, so the base is 81, so that's going to be the base of my exponent. So in other words, 81 to the x is equal to 9. All right, so in other words, 81 to what power is equal to 9? Well, we know that the square root of 81 is equal to 9. And taking the square root of something is the equivalent of doing that number raised to a power of 1/2. All right? So in other words, the solution for x is that x must equal 1/2. All right, so using exactly those same techniques, basically just, again, going back and forth from exponential to logarithmic, and, you know, in the case of something like this, the technique of just setting the logarithm equal to a number, x, an unknown number, then converting to exponential. I want you to pause this now, go ahead and try to solve these 4 problems, and then I will come back with the solutions for you. All right, so I've already gotten our relationship written here above the problems that we're going to solve. All right, so we want to start with this one. Log base 4 of x equals 3, therefore x equals what? All right, so this is already in the logarithmic format. So in other words, we have 3 equals log base 4 of x. And we want to convert that to an exponential equation. All right, so the base of the log is 4. That's going to be the base of the exponential equation. All right, so 4 and then y is 3. 4 cubed is equal to x. Okay, easy. X equals 4 cubed. 4 times 4 times 4 is 64. Okay, so in other words, x equals 64. All right, let's move on to the next one. Log base x of 1000 equals 3. All right, exactly the same. We're in the logarithmic form, so let's come over here. So in other words, we've got 3 equals log base x of 1000. And let's convert that to an exponential form. All right, the base of the logarithm is x. That's going to be the base of the exponential. Okay, so x raised to the y is 3. So x cubed is equal to 1000. So what number cubed is 1000? Well, it's 10, because 10 times 10 is 100 times another 10 is 1,000. Therefore, the solution is x equals 10. Okay. All right, number 3, find log base 8 of 64. All right, so we create the logarithmic equation by just setting this expression equal to x. So now there's our logarithmic equation. All right, so let's write that over here. So we have x equals log base 8 of 64. And now let's convert that to an exponential equation. All right, the base of the log is 8, so that's going to be the base of our exponent. So we're going to have 8 raised to the x is equal to 64. All right, and we all know that 8 squared equals 64, therefore x must equal 2. All right, number 4, find log base 5 of 1 over 125. So just like we did above, we create an equation by setting that equal to x, and we want to solve for x. All right, so let's just write this underneath here. So we've got x equals log base 5 of 1 over 125. And let's rewrite that in exponential form. All right, the base of the log is 5, so that's going to be the base of the exponent. Okay, so 5 raised to the x is equal to 1 over 125. Okay, so all right, so 5 cubed equals 125. But what I want is 1 over 125. So in other words, the way to get that would be if we had 5 to the negative 3. Because 5 to the negative 3 means 1 over 5 to the positive 3, which, yep, that works, because then we get 1 over 125. Okay, so in other words, x must equal negative 3. All right, last topic for this section is something called the common logarithm. Okay, the common logarithm is defined as log base 10. Okay, so in other words, if you just see log base some number, but there's no base written to the log, what that really means is log base 10 of A. Okay, but because log base 10 is so commonly used, we just don't write the 10. So again, if you don't see the base written, the 10 is implied. It's kind of like if you write the square root symbol. And if there's nothing written there, it's implied that it's a 2. All right, that you're taking the square root. Again, it's just so common that we don't write the 2. We just use the square root symbol. All right, so here's what the graph of the function looks like. So this is f of x equals log of x, or in other words, log base 10 of x. And if we just look at the graph, we can see, well, what is log of 10? Well, in other words, if 10 is the input number, okay, So here's 10. Well, we can see that the output number is y equals 1. Okay? Because, you know, we've got that point 10, comma 1 on the graph. And, you know, if we were to write that, okay, well, y equals log base 10 of 10, or just log of 10. So then what does y equal? Well, if we come up here, all right, so y equals log base 10, oh, sorry, log base 10 of 10, and then convert that into an exponential equation. All right, the base of the log is 10, so that's the base of the exponent. Y is just y, so we're saying 10 to the y equals 10. Well, obviously then, y equals 1. Excuse me, okay, because 10 to the 1 equals 10, okay? And also, this is the same as the property that we looked at previously on page 22 of the notes, which says that log base A of A is equal to 1. Okay, so that one was, you know, log of 10 was easy to find on the graph because it's a nice, neat integer point on the graph. But what about finding other values of the common logarithm, or log base 10? Well, for that, just get your calculator out if you don't already have it out, and find your log button. Everybody has a log button on your calculator. It probably says exactly that, just log. And again, that means log base 10. So go ahead and try to use your calculator and try to calculate log of 20. All right, if you do that, you should get something like 1.301. I'm just going to round off to 3 decimal places. You know, the number continues after that. And if we look at the graph, okay, so if the input is 20, here's the log, and yeah, that looks about right, about 1.3. All right, so take a moment with your calculator and find the common log base 10, to 4 decimal places of the following numbers. All right, so what you should have found is the log of 0.25 is about negative 0. Okay, that's a 0. 6021. And we can kind of see that one on the graph. Here's 5, 4, 3, 2, 1. So 0.25 is about here. So that point is about here. Okay. Log of 5,486 is about 3.7393. And we can't see that on the graph, obviously, because 5,000 something is way out here to the right. But what you can see is that the logarithm function increases very, very slowly, because we're all the way out here at almost 5,500, and the y value has only increased to about 3.7. And what you should have seen if you did tried to do log of negative 92 on your calculator is basically it does not exist. So you probably got some kind of an error on your calculator, and the reason is you cannot take the logarithm of a negative number. It's not in the domain of the function. All right, I am going to stop there.